Shown in the figure below is a parallel plate capacitor. The area of each plate is 1 square meter, and the separation between the plates is 1 millimeter. The region between the plates is filled with a dielectric material of dielectric constant K equals 2. And we are to find a list of quantities: the capacitance of the device, if it is charged, what is the voltage difference and electric field, how much energy is stored in this capacitor, and in what form is the energy stored. These are all good questions, and one way to solve them all is to simply look up the formula for each one of the quantities and plug in numbers. That's not particularly instructive and doesn't lead to a deeper understanding of what a capacitor is and how a capacitor works. For that reason, we're actually going to derive the little formulas that we plug numbers into and then plug in the numbers so that we can learn more about a capacitor. When we deal with problems involving electric fields and potentials, we always look for the easiest entry point to these calculations because we know we could get from field to potential or from potential to field. If a problem is amenable to a Gauss Law solution, then Gauss Law is invariably the simplest way to get to all of our answers, and this problem is amenable to a Gauss Law treatment. Gauss Law always begins by using our imagination to figure out the shape of the electric field lines. What we see in this problem is that since the positives are on the left and the negatives are on the right, since field lines begin at positive and end at negative, the electric field lines will be confined to the region between the capacitor plates. For the most part, the electric field lines will be straight as shown here. However, we recognize that at the very edges of this capacitor, the electric field lines will tend to bulge out. We'll be solving for the capacitor in the usual approximation that the separation between the two plates is very small compared to either the length or width leading to area of these plates. In that case, the distortion due to the edge effect will be neglected as though it didn't even exist. We'll be finding the electric field at a center point located by the green dot, and as always in a Gauss Law problem, we ask what other locations have the same electric field, and they're going to make a sheet in the interior of the capacitor. We have to close our Gaussian surface, and we will do so by exiting the capacitor to the left, so that our Gaussian surface has in fact contained the entire left plate. We'll then set up what I like to call the easiest Gauss Law problem in existence. Gauss Law problems are always solved by substituting what is the area of the appropriate surface and what is the charge enclosed by this surface. The thing that makes the parallel plate capacitor so simple is that the area of the right-hand surface, the only contributor, is equal to A, and the charge inside is equal to Q. What could be easier than this? The area is A, the Q is Q, and we get the answer. Electric field is charge over epsilon naught times A, and we're done with our electric field calculation. Whenever we've determined an electric field, we can then calculate the difference in potential between any two locations by integrating the electric field. Delta V is e to the minus E dot dl. We'll integrate from the left plate to the right plate, and E is a constant. So our delta V simply turns into the value of the electric field times the length of the integral, which is a distance d, yielding the result that V is QD over epsilon naught A. Please note at this point that I have been purposely sloppy. I have dropped the delta using slang for the V, and because I know that I can get the sign of the voltage right, I've dropped the minus sign too. That makes the calculation especially simple because all I want is the value. Finally, we recognize that since V equals Q over C, the previous formula tells us that 1 over C is going to be equal to everything on the right-hand side of the equal sign except for the Q. So that 1 over C is D over epsilon naught A, meaning that C is epsilon naught area over D. Tragedy! Oh no! Oh no! Oh no! We totally forgot about the dielectric. What shall we ever do? What you do in the presence of a dielectric is very simple. You simply find every epsilon naught and you replace it with K times epsilon naught, and then you have the correct formula. Meaning that we can repair the electric field to be Q over K epsilon naught times the area. We can repair the voltage to be QD over K epsilon naught area. And finally, we can repair the capacitance to be K epsilon naught area over D. These final three formulas that I'm placing in a box are the ones that we're going to use to calculate the result. For part A, we plug into the capacitance formula and get a result of 17.7 times 10 to the minus 9 farads, which we will call nanofarads. For part B, we plug into the voltage formula using 6 microcoulombs as our charge, and then we come up with the result 339 volts. Finally, for the electric field, we plug into the appropriate formula, and we get 339,000 volts per meter. As the final two calculations, we need to consider the energy that is stored in this system. Although we remember that potential energy of a single charge being placed at some voltage is the value of that charge Q times V, when we charge a capacitor, we know that this process is done sequentially. The very first charge to enter the capacitor enters at 0 volts. The very last charge to enter the capacitor enters at the final voltage. So on average, the charges that are stored in the capacitor experience only half the final voltage. Therefore, the potential energy stored in a capacitor is half Q total times V final. This formula is not inconsistent with the previous one. It's just that we have to recognize what the quantities mean. In the previous formula, the Q was a single charge placed in the potential at the time. Now we are considering the total charge placed as compared to the final voltage. And because they don't all come in at the final voltage, that's where the 1/2 comes from. Using our 6 microcoulombs, as well as our final voltage of 339 volts, we're going to find that the value is 0.001 joules, or 1 millijoule. The last part of this problem is to determine in what form the energy is stored. There is nothing that I have taught you at this point in the class that assures you of what form the energy is stored in. We will learn that when we study electromagnetic waves. Nonetheless, what I have simply told you in an unconvincing way is that the energy is stored in the form of an electric field, because electric fields are real, and the presence of an electric field anywhere in space represents an energy density in joules per cubic meter. And this ends our analysis of a single parallel plate capacitor.